Using the acid from the previous problem, we're going to begin by titrating this solution with a 0.1 molar sodium hydroxide solution. So, when working titration problems, we have to take into account two things. One, that these are really just limiting reagent problems, so we have to figure out how much of the reactants are left over after the neutralization reaction has occurred. Then we move on to determining the equilibrium conditions after the initial neutralization reaction has occurred. So to begin this, we're going to start off by taking our acetic acid and reacting it with the sodium hydroxide. And we need to write the balanced chemical equation because we need to make sure we know our mole-to-mole ratio. Now in a neutralization reaction, this isn't equilibrium. The equilibrium constant is so large on this that it's essentially a one-way reaction. That is, there's not going to be any backward reaction occurring here in which we'll go back to forming our original starting materials. And in the balanced reaction, we can see that one sodium hydroxide and one acetic acid combine to produce water and sodium acetate. So we need to figure out how much material we're starting with. Well, we know initially we had 25 milliliters of our acetic acid. And this acetic acid, which is going to be AA here, has a molarity of 0.1 molar. That is, for every 1 liter or 1,000 milliliters, I have 0.10 moles. So we can work this out and find out that we have 2.5 times 10 to the minus third moles of acetic acid. Well, now we have to look at how many moles of base we have. Well, this problem says we've added 5 milliliters of base, sodium hydroxide, and just like before with the acetic acid, we see the concentration is 0.1 molar, so for every 1 liter or 1,000 milliliters, we have 0.10 moles of our sodium hydroxide. So we can determine that we have 5 times 10 to the minus fourth moles of base. All right, so now we know how much of our initial material we have. Well, we can't compare acid and base. We have to get moles of acid into moles of base or moles of base into moles of acid. But we know from the balanced equation, for every 1 mole of acid I react, I also react 1 mole of base. That is, this is the mole-to-mole ratio. So we can look for the limiting reagent based off of which material we have in the smallest amount. Now between the two, I could either change our moles of acid to base or our moles of base to acid. And in this case, I'm going to decide to work with the moles of base because it's the smaller number. 5 times 10 to the minus fourth moles of base, and because we know for every 1 mole of base, we get 1 mole of acid reacted, so we know we have 5 times 10 to the minus fourth moles of acid that have reacted with the base. So let's figure out how much is left. Well, I had 2.5 times 10 to the minus third moles of acid initially. And I've used 5 times 10 to the minus fourth moles of acid by reacting it with that base. That is, I have used 0.5 times 10 to the minus third. This right here is the same as this. I've just changed it over so I can do my subtraction with the same base 10 unit. acid reacted. And what we find is after this reaction, we now have 2 times 10 to the minus third moles of acid left. So after the reaction, we have this many moles of our acetic acid. And what we also have is product. We made some water. We made 5 times 10 to the minus fourth moles of water. We made 5 times 10 to the minus fourth moles of sodium acetate. But the reaction is done, which means the moles of acid are now allowed to equilibrate in solution. So we can take our acetic acid and allow equilibrium to come in and establish itself. At which point we can set up an ice table to determine the pH. Now, if you like ice tables and you like going through doing these quadratic equations, that's fine. I'm not so hot on them. I prefer to be able to do these as quickly as possible. Nothing wrong with, people that like to do quadratic equations, but my time is precious, and so I typically take a different approach once I get to this point in trying to figure out what the pH is after a base has been added to the solution. And the quick and dirty method that we can use is based off the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation says, look, the pH of a solution is equal to the pKa of the acid plus the log of the ratio of the conjugate base, in this case the acetate, to the acid itself. Well, pH is equal to negative log pKa. Well, what's pKa? It's the negative log of Ka. And if we go back to the beginning of the problem, we can see that our Ka value is 1.8 times 10 to the minus fifth. So negative log 1.8 times 10 to the minus fifth plus log of the base. Well, in this case, the base was 5 times 10 to the minus fourth moles of sodium hydroxide. And we can see here that one of the things that we get when we do this neutralization is we get some acetate ions paired up with sodium. Now, sodium acetate is completely soluble. It's a strong electrolyte solution. Therefore, it's really just sodium ions and acetate ions floating around. And so what we can do is we can say it's the log of C2H3O2 minus over HC2H3O2. And in this case, it's the same as saying plus log 5 times 10 to the minus fourth over 2 times 10 to the minus third. That's equal to the negative log of 1.8 times 10 to the minus fifth. And calculating for the pH, I get a pH of 4.14. So the Henderson-Hasselbalch equation can be used once the titration is started all the way up to the equivalence point. So we can't use it before the reaction has occurred. That is, we can't use it for just an acetic acid solution. But we can use it once we've added a little bit of a base, all the way up until the point at which the sodium hydroxide moles is equal to the number of moles of acetic acid.